talking about. This is in reference to question number 16. The D0 on this curve for curve A. The D0 for curve A, this curve. What's the D0?
Do you want me to read out the options?
Yeah, I can't look at both at the same time here.
So the interesting mixture of rads and centigrade, but 1 centigrade, 10 centigrade, 200, 500, or 1,000. So where does
there's almost you can almost answer this question without looking at the curve. You can almost answer it without looking at the curve, because we gave you in the textual material what the general range of D0s of cells are. The general range of D0s is, for most cells, let's say 50 to a couple hundred rad. And I know there's someplace in your text that says something like that. It's going to give you a general range of D0s. Most mammalian cells have a D0 of. So you can answer the question without even looking at this. But let's look at it and see if it's right. Let's see if it matches for this survival curve.
And you might find it easier to just draw on your paper graph.
Let me show you how I would do this. The straight line portion of the curve is this small dashed line and dotted line right here. So that's the straight line portion of the curve for A. So if I want to know 37%, I need to find a place where I can identify 37%. That's pretty close right there. So I'm going to use that, even though that's not quite precise. I'm going to say I'm going to go from there. 37% of that is right there. All right? So those are my two reference lines. I'm going to drop lines down. I'm trying to draw that straight down to the origins, or to the axis. Actually comes out pretty good. All right? So this interval here is supposed to be an arrow. Represents D0.
And it's 200 centigrade.
All right. I could measure it anywhere. I could measure it from here, the intercept, down to, well, it's about here. And I'd be coming from, I can't get the thing to go straight, but about here to about here. This is also 200. Here. You can draw the straight line anywhere you want. I mean, it's going to be in one place, but you can measure anywhere along that straight line. Yes?
I was going to say, wherever you pick your first intercept, then the second one is 37% of that number?
Yes.
Yes. But it's easiest if you pick it on if it's a graphic model, a graphic representation. It's easiest if you pick it on a 1 or a 0.1 or then you go from 1 to 0.37 or from 0.1 to 0.037. Okay? You could pick it here in the middle of nowhere, but then you'd have to take this number, which let's say is 0.6, take 0.37 of that, whatever that number is, and draw your line across there. And that's just more trouble than it's worth. You could do it anywhere, but use the reference lines. It's real easy. We give them to you. I think any diagram you're going to have is going to have enough information on the axis for you to pick one. You could do the same for this one over here. And let's take this one. Let's take this line here, and I'm going to extend this on over now.
Recognize that what this is actually 1 over E, where E is the exponential. And it simply falls out of the formula as 1 over E. And E is 2.3 something, so 1 over that is 37%.
For line B, if the question's asked for line B, what the D0 is. And it's a little hard with the pen on a screen like this to move it, but I've drawn the 0.1 line over to here, the 0.3037 line over to here, drop my intercepts, 1400 to 1850. So it looks like 450 or something like that. That's a very high D0. You could find that for anoxic cells or under radio protected conditions, things like that. But it's not a typical mammalian D0.
While you're at that, why don't you do the DQ of that line as well? Because that's
Okay.
the next question.
So the DQ of B or A? Either one? Let's
B.
do both. Let's do B. Okay. So the DQ is based on this extrapolation here, which actually is a continuation of the exponential portion. Oops, my hand hit the rail here. This curve. It's about 600 for B.
500 is the
I can't.
answer.
Yeah. Well, my lines drift a bit here, but I mean, if you had a square on here, you could say it. I mean, what is there? Well, it's not 100 and it's not 1,000. All right. It's we tried to pick the answer so you really can't get it. If you know close, you're going to be right.
So
Explain that a little. Yeah.
Okay. This distance from here to here. This is the intercept of this straight line here. So it's a representative of how much sublethal damage is being accumulated. The DQ is from here to here.
It's the extrapolation of the straight line portion of the curve back to 100% survival.
And if you look for curve A, the blue line, we already have an intercept here that drops down to about 400. So for curve A, the DQ is about 400.
So do the extrapolation number for B if everybody's happy with that.
Okay. So what's the extrapolation number for B? Somebody give me their thumbnail estimate.
Remember, it's a log scale.
Here's 6. Okay. I'll buy 6. Something like that.
That's the answer.
Oh, that is the answer. I didn't look the paper.
Well, it gives you 0, 1, 6, 10, or 5.
Well, 0 is, there is no 0, by the way. There is no such thing as a extrapolation number of 0. The lowest extrapolation number you really can have, I can't think of, I guess you could go below the line. I don't know how you do that. So the lowest extrapolation number you can have is 1. So it's going to be greater than 1. It's going to be some positive number. So here's 1, here's 10, 100 would be about here.
If you go below the line, then you've got to have hormesis.
Right. Radiation is protecting you, making you better.
There's some evidence that low doses do.
Yeah, that's strange. What's the extrapolation number of A? Probably more like 20 or 30. Okay. See, 13 would be real close here because remember this is a log scale, so it'd be about 3. This distance from here to here is 3 times this number. So this distance from here to here would be about 3 times that number. So that'd be around 30 maybe right there. It's more than 10.
Right, and the next unit on there is 100.
Yeah, this would be 100 up here. Would be up here someplace. Does that make sense to you? Does it ask any more about this, Graham?
It asks the radiation source most likely to generate curve B is A, neutrons, B, protons, C, hard X-rays, D, alpha particles, E, none of the above. Well, it's got a shoulder, and 3 of the radiations there are high LET radiation, so it's a pretty trivial question.
All right. It has to be a softer radiation. It's not talking about if you were talking about a neutron curve would look something like that. You notice it's steeper than either of these. It may be almost parallel to this A. The D0 for this and this curve are very similar. The D0 between curve A and we'll call this curve C are almost the same. But one has a shoulder, the other one doesn't.
And that turns out to be historically very important, because as soon as the first cyclotron was built at Berkeley in the 1940s, a physician named Robert Stone decided that he would try doing therapy with the neutrons from that machine. They'd never used neutrons before, so what they did is they simply corrected for the relative biological effect. They knew that neutrons were going to have a greater effect per unit dose than X-rays. But they didn't realize there was no shoulder on the neutron survival curve. Now, that is very important in radiation therapy, because if you're going to give a tumor 7,000 centigrade, you don't blast it with 7,000 centigrade all at once. You give 2 grade centigrade, 200 centigrade, 2 grade fractions every day. And you do that for, 14 weeks or whatever. Why do you fractionate it? You fractionate it so that the normal tissue can recover, can repair. And the measure of that repair is the shoulder on the survival curve. So if you fractionate X-rays, you get a fair amount of repair because of the shoulder. If you fractionate neutrons the same way that you fractionate X-rays, you don't get any repair. And what Stone did, he got some fairly nice tumor responses with his neutron irradiations, but he created some awful normal tissue damage, deep ulcers that didn't heal, simply because he didn't know that neutrons don't have a shoulder on the survival curve. And that queered the therapy community on using neutrons for probably 20 or 30 years. They got a bad rap because they cause lousy, nasty, normal tissue damage. But what you have to do is, you have to leave a much longer period of time between the fractions for the normal tissue to repair if you use neutrons. Either that, or you use a much lower dose per fraction so that you don't cause as much normal tissue damage. So that's the relevance, this sort of analysis is the underpinning of what drives the clinical therapy.
Now, I think the very next unit, if it's not the next one, it's the one after that, after this unit 2, at the next set of slides, is going to talk about fractionated radiation and why therapeutically that's important. And this is basically I tried to do it real quick on freehand, but if you're giving doses, 200 rad fractions, let's say small fractions, and then you rest, let the repair occur, then you give 200 again, you recover the shoulder. So you don't ever get to this straight line portion of the curve. You get a little hit, and then it recovers, then you do the shoulder again, then you do the shoulder again, then you do the shoulder again, then you do the shoulder again. So for the same total dose of 1,800 rads, you have this biological effect if it's fractionated, and this biological effect if it's given single dose. Much, much more. But with neutrons, what Dr. Sharp was saying, if I had a fractionated, unfractionated, we'll call this fractionated, but the unfractionated curve would run on exactly the same course. There wouldn't be any difference between the two of them. So that's why those patients were seriously hurt, because they thought there'd be some things they'll fix up a little bit between there, and they didn't. And therefore, the patients were really badly hurt. And we take advantage of it in other ways, too. Tumor cells don't repair as well as normal cells. So if you fractionate doses, you allow the normal tissue to initiate its repair processes, fix some of the damage. The tumor cells are sitting there struggling, trying to figure out what hit them, and then you hit them again. So the tumor cells will not show quite this much of a change. They'll be more like this because they don't repair as well. So you get a differential effect between normal tissue and tumor by fractionating. So that's to the clinical advantage of the therapist to break the doses in pieces because the tumor cells can't repair as well, and that's a kind of an understatement, but that's basically what it is. And the normal cells do, and you get a better survival of normal cells. Not that you don't damage normal tissue. You all know you do. If you're around therapy at all, you know you get red skin and all kinds of things can happen. So they still are damaged, but they can recover most of it. You also do other things. You come in from different ports and focus all your radiation, but that's another piece of it.
I mean, the extrapolation of that curve is hyperfractionation, where you give really small fractions every hour.
Right.
What happens, though, is in a practical situation, you run into the logistics of having to treat a whole bunch of patients, having to spend a certain amount of time setting every patient up, and then there is a limit in most settings how many times per day you could deliver a fraction of radiation to the same patient. But there have been attempts at hyperfractionation, and it probably does work. It's just a logistical nightmare.
Okay, we're out of time. Are there any other questions about